Right, I started the recording. So we were in module number two. Hmm. All right, we are in module number two, right? Everyone, in last class, this is what we have done: surface energy balance. So we've seen the relationship between thermo and heat transfer, right? So thermo is what? Thermo is the energy balance. First law. We've seen that. I mean, all through thermo, right? Whole semester. First law. Everyone took thermo? Okay. So the first law of thermo, we connect it here with the heat transfer by just simply implementing those three equations for conduction, convection, and radiation. Remember that? You might have done it already on the homework. Everybody done the homework? Homework number one? All right. Does the homework number two is already over there? Did I upload homework number two yet? No. So I'll do it today, I guess. And if we do end of this week, something like that. Now, come back to the topic. So in last class, we had two agenda. One is to introduce that. Another one is finish the math problem and homework on hints. Okay. Any question with the surface energy balance? No. It's good. We even had a quiz in last class. Okay. Every day we will have a quiz. If you miss the class, you're gonna lose the quiz. Okay. So just move on to today's agenda. What we'll be doing? We're going to finish up this module two, thermo and heat transfer relationship, the theory part, and I just have one math problem, okay, on the same very topic, at energy balance surface, okay. The question is do a little quiz, see how much you remember. Those who missed the class, did you guys watch the video lecture? Yes, and any question in the video lecture? Okay, perfect. All right, now come back to this. This is the verbal quiz. This time I don't wanna. I don't wanna do like paper. Let's see if you remember. So if you have a surface energy balance in a control surface, uh, what do you have in energy balance equation? Do you have? Let me tell you like different options. Do you have energy in? Do you have energy out? Do you have energy storage? Do you have energy generation? Again, the same thing that you're seeing here, right? At the surface, we had a control surface. How do you know control surface? You see the dotted line? That's referring to that surface only. Do you see on this sketch? Everybody? You want me to make it a little bigger? Okay. So this is the surface, right? So at that surface, we have these two dotted lines, right? One is inside of the wall, another is the outside of the wall. Now that line, dotted lines, I would say, referring to energy in, energy out, or energy in, energy out, energy generation, energy storage, everything. What do you think? Two options. Okay, let me ask you this way. On that surface itself, do you feel like there could be energy storage happen? No. Okay. On that surface, do you feel like energy generation can happen? No. That could be. I mean, if there is any, chemical layer making some heat or whatever. But ideally, no. Excuse me. Ideally, no. Thank you. So ideally, no. So that's your clue. Whenever you're dealing with this surface, energy in equal to energy out. Okay. Now in the homework problem, obviously you've done that, right? Energy in was like probably conduction, energy out was probably like convection and radiation. Now this in and out for these three different modes completely different depend on the temperatures, right? Based on like whether the conduction happened as energy in or based on like the temperatures dictate the conduction the opposite way, like energy out. So it only depends on the temperatures. Any question on that? You guys remember those three equations, like conduction, convection, and radiation? We've done it in last class. If I'm gonna say you write those three equations, can you do that right away? from your memory, everyone? If you are not that state that you can't write this equation, that means you are falling behind on this class, okay? But in week 3, the first class, you should be able to write those equations from your memory because you have done it like so many times in class, okay? Make sense? So just to give you a point like where you are in the class, right? If you can do that, that means you gotta take it seriously, okay? So I was saying, like, I'm gonna quickly go through on this module, okay? And our main goal, by the way, is not to deal with this theory all through the class because we are done almost the main thing on the theory on this class, on this topic, right? Our main goal is to do the math. Just keep it in mind, okay? Do the math for this topic, okay? All right. So we have this module 2, right? Over here, we have this, control volume application in thermo. We have seen that, right? Energy in, energy out, and energy storage, energy generation. Everybody see that? Those are related with this equation, right? Energy in minus energy out plus energy generation equal to energy storage. We've seen that, right? Then for a time interval, that dot term will gonna go away. Do you know for time interval what happened? The dot will gonna go away because you just multiply with the del t, right? The time interval. What is the unit for this one? Watt, right? Or joule per second. What is the unit for this one? Joule, right? You guys remember that? All right. So then, obviously, this can be further deduced for a closed system and open system. This is for a closed system, right? This equation, we have seen it in thermo, and we can further deduce it for an open system. You see, this is for an open system, and this equation, we have learned it in thermo, right? I don't want to go through the same thing because we will not going to particularly use this equation here in this class, okay? I'm just trying to build a relationship with thermo and the heat transfer, which we have seen in last class, and even in today's class. I'm first reviewing the equations for closed and open system, first law, right? And then finally, we've seen the surface energy balance, where this thing happened. In last class, we really didn't have time to show those slides. That's why I'm quickly going through. Again, what did I see? What did I show you first? Remember, the first law for open and closed system, okay? And you have energy in, energy out, energy storage, and energy generation. Those 4 things. Those are review, okay? If you have any question on those things, come talk with me in person, okay? I'll try to give you the understanding on thermo again, okay? But these are all from thermo. Any question? Everything's good? All right, moving on. Okay, so you see there are some maths here as well for your reference. Just please go through those maths, but I'm not going to do any of them. I have this thing here. This is from the last class. This is from the last class. Yep, I have this math here, and I have this theory here. Now, I know when I said something, if you don't write it, most likely it's flying through your head, on the top of your head. So let's do those equations one more time. We're going to write that, take that class note, okay? And then we're going to do the math. Whatever I just showed you. Any question? If you guys, okay, let me know, okay? Otherwise, I don't know. So why don't all of you start taking the class notes, okay? Let me get my class note here in my end. Okay, so let's start with this sketch. You're seeing a bean kind of shape here. Obviously, the bean is referring to any control volume. It could be anything, okay? So it's arbitrarily shaped this way. You don't have to draw the bean or anything. You can just simply write the text, what am I doing. Remember, the PowerPoint that I was showing it to you just before is in Brightspace, okay? You can't have the OneNote access, but everything is in Brightspace, okay? So you just want to take the class note from here so you can connect. So if you start to draw everything that you're seeing, you will not gonna have enough time to finish the class notes, and you'll lose your precious time in class. Does it make sense? You just want to write the theory that I'm doing here, just to give you a heads up. All right, so what I'll be doing here, the rate equation. Okay, so I'm doing the control volume first law, conservation of energy, and over here we have the energies coming in, energies coming out, and energy generation and energy storage inside the bin. If you have a dot on the top of any of this term, what does it mean? I said it in last class. If you have a dot of any of this term, means like these parameters that we're seeing E, that what does it mean? Dot, the rate per unit time. Remember that, right? If you have a dot, per unit time, that's universal for any subject, any book. Anytime you see a dot, what does it mean again? Per unit time. What is the unit for that? Joule or what? Watt. Per unit time means what? Joule per second, right? Okay, so let me write it. So E in minus E out. I know for some of you this could be a little silly, and for some of you this is like very important. Okay, so if you feel like you are really expert on whatever I'm doing, please just ignore what I'm doing. But for some of the students, I know this is really crucial. They might forgot the um, you know thermo, or they did it long ago, so they don't recall now. Bottom line is so important for some of the students. So you see here, you have energy in minus energy out plus energy generation equal to energy storage. Okay, and you have this dot term refers that it is per unit time, and the unit should be watt or joule per second. So where E dot in is energy in, E dot out, you'll be feeling excited from next class when I'll be started dealing with the Fourier law, like the differential equation. Okay, so energy out EG, that's module number 3, energy generation. Finally, E dot st means energy stored. By the way, this is the same as E dot st. Okay, okay, for over a time interval, as we've seen, right? So for over a time interval, you gotta multiply with del t in every terms, right? So then you'll have this thing as E in minus E out plus EG st. Okay, so that's the summary of what we have seen in the slides. Again, what we did so far is just the first law. I'm writing it in rate term and non-rate term, generic, right? It doesn't specify closed or open system. It can close for any of the systems, right? So the next slide that I have is for the first law for open system. Okay, any question on that? Everything good? Perfect. Let me know when you're done writing so I can move on. Now the problem is, and please try to write a little faster. Okay, the problem is this system that we are having now. I explained why we can't share this OneNote, right? Because it's a federal law. So anyway, so the problem is you don't have the access, so you have to write it during the class, whatever is happening here. Okay, we have another way around the video lecture, which I'm putting the YouTube video link, right? So you can do the subtitle along the way, but in class you'd like to write a little faster. Okay, anyway, so then we have this open system and closed system. Now I said that equation is generic, right? First law. So for open and closed system, you can write the same equation for open and closed system this way. Let's do it this way. So like for open system, you have energy in minus energy out, right? Plus energy generation equal energy storage. So energy storage, you can write it this way. And if we have some assumptions, say like steady state, let's see how much you remember from thermo. Which term can be go away? There are 4 terms: energy in, out, storage, and generation. Which term is going to go away? There are 4 terms: energy in, energy out, energy storage, and energy generation. If we are dealing with SS means steady state, everybody remember, right? So if you are dealing with a steady state situation, energy storage, energy generation, energy storage, because steady state means what? Like there is no way you can store the energy with time. Okay, so steady state means with time no change. Always remember. Energy generation is dependent on the chemical or nuclear reaction, whatever is happening. So that's a function of those extra material, not the time. But energy storage is a function of the time. Does it make sense? Just like think this way: mass storage. It's easier to understand that way. Say like you are taking a shower in a bathtub, right? So like you open the faucets and the draining happening at the same time. It's a slow leak you have, or not the leak. It's a slow drain. You are opening it such a way so like the amount of water that is coming and amount of water that is going needs to be balanced. What if those are not balanced? That means say like more water is coming, less water is going draining. That means energy water level is gonna keep up. That is the energy generation happening. Sorry, energy storage happening over the time. Yeah, not the junction. Energy storage happening over the time. Everybody got there? So that's why, like, with time, if the amount of water coming and amount of water going is the same, then it's the mass balance. That was the mass balance thing. I'm doing analogous thing here with the energy balance. Does it make sense? So if amount of energy that is coming, amount of energy that is going on the surface is not same, then the storage can come. If it's same, then there is no storage happen. Does it make sense, everyone? So steady state. I mean, I was hoping everybody should tell like right away, like steady state means energy storage is zero. Everyone's gonna remember it from now on, right? Whenever I said steady state, that means what? Which term go? Energy storage. Okay, I was hoping everybody remembered that. Okay, please remember that. Energy storage go away. So the other assumptions you can do, energy generation is zero, like there is no chemical reaction or nothing is happening, right? Energy generation will go away. So you do have like these 2 terms only for operating system most of the time. What are those? Energy in and energy out, right? So let's focus on that. So I was just saying about this energy generation is go away. So energy generation is zero as well. So this is your 1, 2, and then you have these 2 more assumptions. So like change of kinetic energy and change of potential energy is zero. Now you see that del is referring always change. Everybody remember that. Like PE is potential energy, KE is kinetic energy. We've seen it in thermo like extensively for weeks after weeks, right? These 2 assumptions. So if you're gonna do all those, then this equation will gonna become energy in minus energy out equal to not all those first 2, right? The number third we're gonna apply here. So let's now focus on this sketch here. So what we're seeing here on that sketch, we have an opening here and opening here. On one opening, some amount of fluid is coming, other opening, some amount of fluid is leaving. Okay, so when the fluid is coming, it may come with certain temperature on the fluid temperature. I'm saying, right? So the amount of fluid that is leaving, it may go out with a different temperature, completely different one than whatever is coming out. Okay, so when the energy is coming in with the mass and energy is going out with the mass is different, it needs to be accounted here in energy in and energy out. Does this make sense? That's the mass related energy exchange. When I said mass, your easiest example could be a fluid. So like you have a tank, right? You're constantly adding water, like hot water on the tank, okay? And you are getting like the geyser. I don't know if you have seen geyser, right? And you are draining out that water through a pipe to wherever you are using it for shower, right? So adding water, gaining water, draining water, right? So if you are adding water at a high temperature and draining water to a different temperature, it makes sense what I'm saying? So that means what? That means like the energy in for the mass or fluid that is coming in, energy out for the mass that is going out is different. So you need to account that in energy in and out. That's the mass thing only, right? What are the other source that heat can add it here or the energy can add here? Think this way. The geyser example I was giving. Everybody know what is geyser? It's in US it's not common at all because we do have the hot water tank or the tankless hot water, so we get the hot water directly from there. I mean, especially in if you wanna go in like the developed countries, you be seeing geysers. They don't have this. I don't know if you ever experienced. When I go back home, like for visit, I see they have geysers everywhere, right? In every hotel, they're gonna ask, "Do you have hot water?" Because they don't have hot water on the faucet, but you need the hot water during shower for sure, right? So they have the geyser there. So anyway, geyser is like a tank, okay? Over there, see like some amount of water is coming, some amount of water is going out, right? But it's not like you are dumping in hot water and dumping out hot water. Then what is that it is doing? It has some function. Usually, the thing that it does is like it has a heater inside, right? So heater heat up the water. So usually cold water come in, the heater heat it up, and the hot water goes out. Does it make sense? Okay. So here is the thing I'm trying to point out. Remember, the cold water in, hot water out, energy out. That's easy, right? But what if that I have this heater inside? That means I'm not adding any mass to heat up or energy, beef up the energy. What I'm doing, I'm adding the heat, like the Q. Does this make sense? So that's the Q in that equation that you're seeing on the top of the sketch. That Q is coming in. Do you see that on the sketch? Take a look on the sketch on the top. The Q is coming in. That's the heat from the heater, right? Okay. So usually that geyser is not insulated, right? If it's not insulated, the heater is heating up the water for sure. We will be losing some heat as well of the surrounding, right? You agree? So that will be heat out or Q out. So you could have Q in, Q out. Is it clear? Okay. So now the work in, work out might have effect on the energy as well. But that is usually the easiest way people put it in book is like they have this kind of a turbine blade kind of a thing. They put a fan kind of a thing. They rotate it. So there is this shaft work going on. So that's a work in. Does it make sense? Work out, you remember from thermal class. So if there is a piston moving up and down, okay, so then there is a work out, that way you are giving away the work, okay, but nothing is happening in the geyser case on this one. But you'd be putting them in the equation. Whatever I just said so far is just a review of thermal. Okay, in heat transfer class, you may not use that extensively, but you need to know in case if you'd like to connect it with the heat transfer. So you have this Q in minus Q out. Okay, now you can put a dot on the top of the Q in heat transfer. Remember, the Q, they don't put a dot on the top. Okay, but that's the rate. That's small q. That's what they use. Okay, plus work in, work out. You wanna write this equation, okay? Plus m dot. You may be seeing it in the next step quiz, okay? Hi plus vi squared over 2 zzi minus m dot. You can put a I subscript here, O subscript here, HO plus VO square over 2 ZZO. Now you guys remember what is H? What is H? No one? Thermal? Enthalpy, right? So what is the unit? Kilojoule per kg usually. So m dot in and out, those can be same, right? When? From the mass conservation, right? Remember? We have this altitude goes away because of the potential energy. Velocity at inlet outlet goes away because of the kinetic energy, right? Those are zeros. So can I rewrite this whole equation to this way only? So Q, I can write this as m dot Q in, and here there is no Q out. Here we have a work out happening, so there is no work in. So we can write Q in, work out, right? Plus m dot Hi minus Ho. You guys agree with me on that? That complicated equation became a simple one based on some assumptions. What are the assumptions again? Steady state. Immediate potential energies are zero. No energy generation. Okay. Okay. Almost 20 minutes past that we started this class. What did we learn? Quick recap. So far, we're doing the review only, right? What review we're doing? The first law of thermal, okay, for open system and closed system. We have learned if we have a dot on any term, that means the rate or what, right? These are all review. I keep saying and saying and saying, and I would encourage you to start reading the book. Otherwise, you're gonna fall behind. You're good with it. All right. Okay. So moving on.
What chapter should we get to?
That's the chapter 2. I mean, even chapter 1, depending on the book itself. But you see, whenever you go with this chapter, you look for the relationship of thermodynamics and heat transfer. Okay, relationship of thermodynamics and heat transfer. So the second homework that I'll upload today, every homework we're gonna say like what chapter you should be reading corresponding to that homework. Okay, from what book. So please read through the book on this subject if you'd like to understand anything on this subject. This class time is not enough to understand this kind of subject. Okay, maybe you can get away, but you will never gonna get the full feeling of the subjects. Okay, if you'd like to learn it, really learn it. When I was undergrad, I used to read several books. Okay, that's the proper way of learning. Okay, so the other things barely I can touch upon. Some of the thing is like, okay, how to find this H. So say like you have this enthalpies, change of enthalpy, right? That can be written because this is what you will gonna use. This is what you're gonna use for sure in heat transfer class. So you remember the CP, that's for the ideal gas, right? And you remember H is what? U plus PV. Everybody remember that? What is this B? Specific volume. How many times in thermal class I emphasize on the specific value? David, how many times? Probably 100 times, right? The specific volume. Pretty much every class I started saying, right, Carly? Every class I started saying specific volume. Tell me what is the specific volume, right? Tell me what is the unit of the specific volume. Everybody remember specific volume? Okay, so this H is the same thing U, right? Anybody remember what is U? Internal energy, and the unit is the same, right? Kilojoule per kg. Okay, and what is the P here, by the way? P is the pressure, right? So you remember the H equation? So like, by the way, this PV with this specific volume PV, there is a term for that. Anybody remember what is that called? They call it flow work. Remember that? Flow work, right? So let me write this. This is they call flow work. You did a math, right, in homework with the flow work. I don't know if you recall. All right. So what are the things? This is the change of enthalpy, right? Change of enthalpy. You took thermo before, right? Does it ring a bell? Any of the things that I'm showing? Okay. Perfect. So this is the change of enthalpy. What else? Like this is for gas, but what if you have a liquid? Now, oftentimes you would presume it's an incompressible liquid. Then this Hi minus H0 can be written as the same thing, but instead of Cp, we just have C, like the specific heat. Everybody remember that equation as well? And that's it. Theory-wise, I'm almost done. I have plenty of time to deal with the one math problem that I have in the agenda. I don't want to do 2 math problems, but I should be doing. At some point, you'll be seeing me giving more materials because of the time issue. But for now, at the beginning of the semester, I don't want to rush anything. You might be seeing me kind of talking a little faster on these things because these are the things coming from thermal review. But before I proceed any further, let me know if you have any question. Does anyone have any question? Want me to clarify one more time any of the thing that I just said so far? No? You feel good? Madeline, you're good? Okay. The next one I'm gonna skip because I did it already. This one last class. I don't want to repeat the same thing. We spent probably more than 10 minutes on that, right? So don't want to do that. I mean, it's on record also. If you miss the class, just watch the video, okay? But after this, let me know when you're done with the class note, okay? So I can move on. And move on means like our last agenda for today's class is the math. Whenever you're done, let me know. I have a solution for you guys. Like if you are slow rider and feel like you're in a really long time. If it's like a little bit long time, it's fine. But it's really long time. You see, all the lectures that I'm doing here is on record. I'll upload it right away after the class. So please watch those lectures as well. It could be helpful. Everyone's done? Should I move on? Okay, perfect. And that's when you're gonna feel excited for sure. When I'm doing the math, I know. Let me put the math somewhere here. This is our agenda. Let me read through the problem first. So an overhead of 20 meter long. Oh, by the way, you know the relationship of meter and feet. 1 meter equal to 3 point something, right? So like it's quite a big of long pipe, right? You see 75 feet pipe, insulated industrial steam pipe, 100 millimeter diameter. Okay, so these pipes that you're seeing they are wrapped by some insulation, right? And the diameter of the insulation is given as 100 millimeter, is routed through a building whose wall and air are at 25 degrees Celsius. So what does it mean? So you see air temperature here. Anytime you'd like to deal with the air, you'd like to draw a cloud kind of a thing, and that's the T infinity. That's what you'd like to use, right? And the T infinity and the T surrounding. So the surrounding, anytime you'd like to refer to surrounding, you'd like to draw this L-shaped thing and some hatchet line, okay, for T surrounding. That's the convention, by the way. So they gave you those two temperatures. What are the temperatures for those two? 25 degrees Celsius, right? Let me highlight that. So they said like building wall and air, okay? So those pipes are obviously inside a building. Have anyone ever went to our HVAC lab? I mean, I know pretty much everyone because we had the what project in the HVAC lab. Remember in thermal class? So in the HVAC lab, the reason I said that, did you ever notice on the ceiling how many pipes are there? A lot, right? There are ducts and pipes, not necessarily only pipes, but there are a lot, right? So something like similar what we're seeing here. Now, did you notice like those pipes that I'm referring over there has any insulation on it? No, there is none. There's none. There's no insulation. But there are some pipes, small pipe, those used to come from the boiler, those has the insulation. Okay, and we have a similar situation here. So why? When we are getting we are getting the heat from a boiler and want to transfer it by using a pipe, right? Make sure you have the proper insulation. Just like at home, have you ever noticed at home that you have even the hot water supply pipe has the insulation? They usually put insulation on both of them. Did you notice that? I don't know if you are working for construction, you would have seen. Like I've done remodeling to my house. I've seen everyone on the copper pipes. They put this not for the flax. Nowadays, people use the flax. The flax they usually don't put it, but for copper pipe, they for sure they put it, right? Okay, what was my point? My point was like you see on the HVAC lab, it was good. It was good, right? So the HVAC lab, those pipes that we're talking, has the insulation, right? So what is the purpose of the insulation? Not to lose the heat. Like would like to get the maximum amount of energy out, right? Understand? All right. So you see here, they gave you these two temperatures. They gave you the temperature for those pipes that is carrying the steam, right? They gave you the diameter of the insulation, right? And they were asking, they also give you the value of the H and epsilon. They were asking how much of the heat loss from the pipe. Still, there will be a heat loss, right? No matter how much of insulation you're putting, if you put the insulation, the heat loss will be very minimal. It could be probably 10% if you don't have insulation compared to before, right? But it's there still. The question is, how much of the insulation? Everyone understand the question? Okay, so every time, whenever you see epsilon in the question, what does it mean? Emission, definitely epsilon is emission, but that means that you have radiation there. Anytime you see epsilon given in the question, the question is asking you, even if it's not said directly, question is asking you, deal with the radiation. Don't ignore the radiation. Why I'm saying that? Most of the time, when you'll be doing the problems in heat transfer class, you'll be saying that in the assumption, neglect radiation. But you have epsilon terms given somewhere in the question. If you do that, neglect radiation, you're gonna lose points because you gotta now adopt the radiation in the problem. Any question on that? Okay. Anytime you're seeing there's an H value given in the question, what does it mean? The convection, you got to account the convection, okay? You know that, right? So convection and radiation are there. So on the pipe itself, think about the pipe, right? It's hard to, maybe this could be example. This looks like a pipe, okay? And this could be like insulation. I actually have a pipe with insulation in my office. I'm going to bring it some point, okay? So this is the insulation, right? So they're asking, hot water is flowing inside, right? At hot water means steam, 150 degrees Celsius. They're asking how much of the heat that you are losing, even if you have insulation there. How are you going to find it? Any idea? Think this way. The amount of heat that is coming, through the insulation, right? That needs to go where? To the air, cold air, 25 degrees Celsius. What is the water temperature that is going inside? It says here 150 degrees Celsius, right? The surface temperature. So it's very high, hot water, right? So it will gonna do what? It will gonna, some amount of the heat will gonna lose by convection in the air, right? 25 degrees, and some amount of the heat will gonna lose where? By radiation through the surroundings, means like the walls and everything that around it. Does it make sense? You understand the problem? How to deal with that? So how are we gonna deal with this problem now? We're gonna write the givens, find assumptions, the engineering format, right? And then when we're gonna solve the problem, we'll do the surface energy balance, right? On the surface. So that's what we've done in the homework, right? So we have this conduction equal to convection plus radiation, something similar that we'll be using. Does it make sense? Any question with the strategy or approach of the problem? Everyone understand the problem? Very good? Understand, right? So the heat that is coming in, it must need to go out. What is the way of going out? In the air or in the surface, right? All right. So let's now solve the problem. That's one thing. Okay. So before even you do anything, you would like to draw a sketch of that pipe that we're talking. We have a bunch of pipes here. Not all the pipes we are doing the math. We are doing just a one pipe math, where the length of the pipe is given as L, right? And you do have the insulation here, right? On the top of the pipe. So assuming we have the insulation drawn already, and the diameter of the insulation is given, right? So this symbol is for diameter. Everybody remember that? So that letter that I put it over there. And the surface temperature is given as Ts, right? And they said the air that is blowing around it on the top of the pipe has a H or convective coefficient, and the T infinity is the air temperature. Okay, once you have all the symbols, then you are ready to deal with the givens. Okay, let's start with that. So what are the givens? The surface temperature. So they said the pipe surface temperature is 150 degrees Celsius. So the surface temperature is given as 150 degrees Celsius. Okay, you see, I also pointed out here by TS. And then they said like the T infinity and T surrounding both are same as 25 degrees Celsius. Okay, they gave you the value of the emissivity. I'm writing it. After sometimes I won't be writing the emissivity every time I'm putting epsilon, which is 0.8. They gave you the diameter of the pipe as 100 millimeter, but we want to convert it to meter, right? So 0.1 meter. So they gave you the length as 25 meter. Okay, so you gotta do like this convection coefficient. I'm writing it because the first time I'm dealing with this thing in the problem. So convection coefficient H is given as like 10 watt per meter square Kelvin, right? And there's this other thing they didn't give you directly, but you know that from previous class. They call Stephen Boltzmann constant, right?
Are we assuming it's a black body?
No, because of the epsilon value is not 1, so it's not a black body. Epsilon value 1 means 100%, means the black body assumption is correct.
And we have 80% of the second Boltzmann constant.
So yeah, the 80% means like the 80% of maximum amount of emission that can happen from the surface. That's the point 8 is referring. So Stephen Boltzmann, don't forget there's 2n, I'm assuming, on the Boltzmann. So there's the Stephen Boltzmann constant. The writing a little weird here. Hopefully this will be good now. That's the sigma, right? And it can be written as 5.67 10 to the power minus 8 watt per meter square Kelvin to the power 4, right? And that's the value, right? You'd be using all the time for sigma or Stephen Boltzmann constant. So better if you remember it for this class, at least this semester. I don't forget that. I use it all the time. So 5.67 10 to the power minus 8 watt per meter square Kelvin to the power 4. Okay. So what you're trying to find? So you're trying to find the heat rate, or you can say this is a heat loss from the pipe, right? So heat loss from the pipe. So like if you're gonna do it this way, so heat loss from the pipe. So one is the convection, another one is the radiation. This two form of heat that we are losing from the surrounding, right? So that's what we're gonna find, like the heat loss, right? Q loss. And we're gonna do some assumptions as well in this problem. So what are the assumptions that you'd like to do? Anyone? That's what the theory is for, right? We did extensive theory analysis like first 25 minutes or so. What are the assumptions that you can do? Steady state, thank you. There's no brainer. Anything else come up in your mind on the pipe itself? Is there any chemical involved? Nuclear reaction involved? Nothing. So EG or energy generation, right, is 0. What else? Okay, for now just let me write the temperature on the pipe is same. So you can say like this is uniform temperature, right? Because they said like 150 degrees Celsius. They didn't say like this section or that section different temperatures. So you can assume that as well. Okay. All right. So then you can do what? Like the solution, where you can start to do the energy balance first. So your energy balance, E in, E out plus EG. You see the relationship of thermal and heat transfer here? Equal E storage. Now I can say this one 0, like don't explain the same thing again, you're seeing it, sorry. Okay, so because it's a steady state, right? Did explain, I said this is 0 as well, right? and then I can redraw the same thing like the sketch that I was trying to do. You see what happened in the wall itself, right? There is a wall, the pipe wall, right? You have this Q conduction, and that conduction, we have this convection here and radiation here. Now the arrow is pointing out from the pipe. You know why? Because the pipe has higher temperature than the air and the surrounding, right? What if you have a different situation? Pipe has lower temperature. You'd be gaining pipe. You'd be gaining heat on the pipe, right? Rather than losing heat on the pipe. If the pipe has a lower temperature. Now the pipe has high temperature, right? Because it's steam. What if you would like to give you an example? Like, the refrigerant. Have you ever touched a refrigerant copper pipe? Like in an evaporator, it feels much cold, right? So in that case, that pipe is gaining heat, right? You see what I'm saying? It's not necessarily pipe is giving away heat or losing heat always. The other way it's possible. In practical example, we're seeing it all the time. Is it clear to everyone? Okay. So what are the forms that we are losing heat from the pipe when pipe is carrying this steam? Because pipe is exposed to air. What do you expect heat transfer wise from pipe to air? It's convection, right? Because of air. And the pipe is exposed to the surface, right? Surrounding. So we're gonna lose the heat by radiation. Does it make sense now? So two form. Okay. So let me write that. So you have this Q E in equal E out. Does everybody agree with that? Everyone, right? So this E in is the conduction, right? And this one would be radiation plus convection. Now, here's the thing. You see, I didn't put a dot, but I'm writing the same rate, and I keep emphasizing on the same thing. In a heat transfer book, they use the small q without any dot, but this is still referring to the rate. Remember that, right? Q is referring to the heat rate. Always remember that, okay? It's a small q. Big Q, different issue. But small q for heat rate or heat transfer rate. Anyway, so here what we're trying to find, by the way, we're trying to find how much of the heat that we're losing from the pipe, as I said just before, right? And what are the way we are losing it? One is the convection, another one is the radiation. Now, we know the equations for convection and radiation. Do you know the equations for the convection and radiation? I mean, in last classes, we have done it several times, right? How many times you did? 3-4 times maybe at least. Write it here, did the math. So we have used both equations, right? So why don't you guys write those equations, those two equations. The convection one is again, what is H, or the convection coefficient multiplied the change of temperature, which is Ts minus T infinity. You guys know what is Ts and T infinity? Ever see that? In the givens you write it, right? Did you write the Ts and T infinity? Okay? You write the Ts and T infinity, right? So you know that. You find the convection now. Again, equation is H multiplied Ts minus T infinity, right? Multiplied the A, the surface area of the pipe, right? Where we're losing it. Okay? That's the convection. What is the radiation? You remember the radiation equation from the pipe to the surrounding? Epsilon. Sigma. Area. Temperature. Ts. 2 to the power 4 minus T surroundings to the power 4. Perfect. So now here's the thing. If we're gonna use this degree Celsius on that equation, it is not gonna work. We're gonna convert it to Kelvin. Does everybody understand that? So how to convert that temperature to Kelvin? Do you know? If you're given it, let's say like 0 degrees Celsius, what does it mean? How many Kelvins it is? You have to add 273, right? Which is 273 Kelvin, right? But you don't have a 0 degree, you have 25 degrees Celsius, and you have what? 150 degrees Celsius, right? Can you convert those to Kelvin? Yeah, and can you use them on the equations that we are just talking, like the convection and the radiation? Snap them, and you'll be getting how much of the heat loss or Q conduction, how much of the Q conduction, right? That's actually the heat loss. Can you do that? Everybody can do that problem by yourself? Okay, then finish it. I'll be doing the same. But you don't wanna copy my work. You wanna do it by yourself and match it with mine, okay? What I'm doing. Okay, so I'm gonna put this as a equation number 1, and then I'm gonna write those two equations for convection. You guys also remember CONV means convection, right? There's a short from COND means conduction. We've used it several times also. RAD means radiation. So those are the equation as I was saying to the class. So T surface, T surrounding, and then I have this HATS minus T infinity. And I was saying like, okay, don't forget to convert them to Kelvin, right? So you have these 423 Kelvin. You have this 25 plus 273, which is 298 Kelvin. You have this again 298 Kelvin, right? The same thing, adding to 73. All right, so then you can write from equation 1, right? So this is like the heat loss from the pipe is same as like the conduction, right? Is equal to Q radiation plus Q convection. Everybody remember like CONV, V is for convection, right? COND, D is for conduction. Don't forget about that. The subscript CONV is for convection, COND is for conduction, right? D is for conduction, V is for convection. Okay, so then I'm gonna write those equations and I'm gonna simply plug those values, right? By the way, those who are done, it should be 18.4 kilowatt. If you get that result, that means you're good. Okay, actually you can leave even. If you get this result, understand everything, you can leave. But I'm gonna finish it, the whole thing, whole 9 yards here. I'll just simply plug those equation for convection and radiation, right? And then I'll start to plug all the values. Now here's one thing, one catch, the area, the surface area. Okay, you want to calculate the surface area for the pipe. So for the surface area of the pipe, if you remember, the diameter of the pipe is D, and the surface area can be written as surface area. I'm sorry, I'm writing it on the side. Please don't get confused. This is for the surface area I'm doing here, right? So it is pi dl. Now, where do you get this equation for surface area of a pipe? You know it from geometry, right? Pi dl. You know all those values. So let's just plug those values. So D is 0.1 meter and L is 25 meter. The pipe length and is 7.85 meters square. Why do I do it here? So when I'm just using this A value for the surface pipe here in this equation, you won't be getting confused. So you have this 0.8 here, right? And then you have this 5.67. What is the unit for the emission? Anyone? What is the unit for the emission? It's a unitless, right? It's a trick question. There's no unit for the emission, but there is the sigma unit. I gave it here, watt per meter square Kelvin to the power 4, and then I have 7.85 meters square as the area, right? And I have this TS as like 423 to the power 4 minus 298 to the power 4, and these are Kelvin to the power 4, right? Okay, and then I have this convection, obviously, which is 10 watt per meter square Kelvin. I want everybody to solve the problem like with a unit. Okay, this is standard way of dealing with the math, so you can cancel out all the units and come up with the final units of interest. And then the area is 7.85 meters square, and 423 minus 298 Kelvin. Okay, so let's begin with the unit conversion. So this meter square Kelvin to the power goes away. So we are seeing only watt left, right? The same thing, this meter square Kelvin, and Kelvin goes away, so only watt left. Do the math, you're going to come up with a value of 18,405 watt, and that's your heat loss or heat rate, heat loss from the pipe.